All right. All right. Okay. We're back. So I've got parts on the way for all this, but but we need an enclosure. This enclosure is important because um, this enclosure is important because I have a kilowatt motor with a weight attached at the end, and it has a maximum speed of 3,000 RPM. So I'll let you do the math on that. Um, so that's dangerous. Um, how do we make it less dangerous? Well, we enclose the entire thing in a polycarbonate structure so that, God forbid, if something goes wrong, this thing does not turn into a projectile and instead smacks against a polycarbonate sheet of plastic versus my face or the dog. So that's what we're doing today. And it's tricky. It's tricky because I need to get to this thing. So one of the things they do in the paper is they actually perturb it. So I need to be able to open the door. Once this thing's dialed in, ideally there's essentially access holes so that I can get to it with a broomstick or something to poke at it and show that it can recover with off policy inputs. That's what we'll call that. I think that's the right way to put it. Okay, so what I've done so far is I've drawn the volumes, the interference volumes, if you will, in red here. So I've built an interlocked aluminum sort of substrate for the entire assembly to sit on. We'll have to add essentially some structure there for this thing to be able to bolt together with. Let me hide all this actually, and I'll draw. Actually, do we have? No, we don't have the new Shaper 3D update yet. Okay, so we're going to take a quick screenshot so I can draw on this. So what we're going to do today is build essentially a giant cube, which goes over this thing. If I can remember how to use Excalidraw. Is she working? There we go. All right, so what we're going to do is we're going to build a polycarbonate structure, essentially just sheets of polycarb that box this thing out like so. And that's going to require some angle. Haven't given it too much thought yet, but just imagine some angle here. And that's going to mount essentially the structure all the way around at the base. Additionally, that angle is also going to serve to join multiple parts. So it'll look like this all around. And it'll have screw holes, and it's going to look great. Maybe it doesn't need to go the entire perimeter. We'll just kind of representationally do that. Same story here. Holes, and then finally some holes. Okay, and we need a hatch because like I said, we want to be able to poke at this thing. And a hatch requires hinges. And a latch. And then finally, we're going to build some structure tube, essentially, down here. And it is not officially released yet from Send Cut Send, but we're going to try using some Send Cut Send tubing and not 80/20, because 80/20 is for cowards. It's mostly a joke. Okay, so that's what we're doing tonight. And I optimistically think I can get this done in one sitting. Realistically, I know that I'm going to run into something that's going to make this not happen in one sitting. But I can at least get it sketched out conceptually, and then we can get into the rest of it later. These parts, everything highlighted here, get here tomorrow, essentially, or they ship tomorrow. They'll be here Friday. So all of the machined parts, I already have all of the off-the-shelf stuff behind me. So that's important because essentially I need to get these parts cut and sent as soon as possible, because I'm not going to turn this thing on until I have the safety enclosure ready. I'll build it, but I'm not turning it on until I get the enclosure set up. Now, realistically, what's going to happen is that I'm going to put these parts together, or try to put these parts together, and realize that, hey, the the clearance for this bearing I gave 65 micron radially is not large enough, and this doesn't fit. And so then I'll need time to either sandpaper that away or reorder this part. So I've never in my entire life had a build come together. I've never one-shotted a build like that, or at least one of this complexity. So, and I don't feel bad about that for a number of reasons. One is I had to change the entire pivot design because of some DFM constraints. And secondly, because I don't think Ben Krasnow at Applied Science has ever had his first build work first shot. So I don't think anyone's have. Okay, so all right, so I'm going to turn on this volume. And so real quick, let me explain what's going on. This circular shape and this circular shape represent the worst possible case of the movement of these components about its rotation axis. In other words, I'm saying if you put your hand here, it won't get hit. If you put your hand here, it won't get hit. But if you put your hand here, there's a chance you could hit it with the pendulum. So what I'm going to do is I'm going to then rotate this entire volume. And rotating that entire volume gives you something like this. So this volume here represents where the pendulum can be, which is to say it's the no-go zone. So what we're going to do is we're going to build the enclosure around that volume. You can see I already got started here, and I actually made a polycarb sort of separation barrier from the controls. And I'll route the control cables probably through a channel, maybe through a channel, TBD. But it'll route from here down to the motor and encoders here at the pendulum. So I kind of sketched out what we're going to do here. Let's just get to CAD. Yeah, let's just get to CAD. So we'll design the enclosure first, and then I'll leave the structure for the bottom to later. Let's see, it's essentially 5 o'clock here in Seattle. So if I wasn't streaming, I think I could do this in 2 hours. But talking slows me down. Okay, so we'll hide these volumes and instead assume that since the volume is contained within the perimeter of the of the base, we'll just build to the base, and we know that we have to maintain this edge distance here to ensure that we're not going to get picked up and hit by the pendulum. So what's the distance between the perimeter and the volume? And that is about 2 inches. So we know we have about 2 inches to play with here. About. We'll call it we'll give it 10 of clearance. The enclosure is for this assembly. So if you go to this GitHub, you can see what we're working on here. It's for this. And this paper is a recreation of the work done at Inha University on using reinforcement learning to create a control agent for a double inverted pendulum with a single axis of motion. So you can find that all here in the GitHub. It's a dual inverted pendulum, not just a pendulum. Details. Okay. So okay, let's get going. So right off the bat, actually, we should find out what the minimum or what the maximum part size for a sheet of polycarbonate could be, because that's going to drive a lot of the decision making here. So let's say, for instance, we wanted to make it out of a single sheet, which would be easiest. Double pendulums never spin in a perfect loop. The line never connects. I don't know what you mean. If you spin only this pendulum, this is the maximum area. This is the maximum volume it can create. Assuming that, yeah. And then same here. And then this volume here is what happens when you rotate that. Okay, so let's get back to this. So let's say we wanted to make this out of a single sheet. What would that have to be? Let's turn that back on. So we would need, pull up the sketch here. So we would need essentially to come up here and across. I know that this is going to be bigger than the maximum allowable, but I just want to get a sense for just how much bigger this is than the maximum part allowances. So we'll call this, yeah, 800 is good, actually. So we need it to be 800 by 1 meter. 800 by 1,000. So we can actually go check now. Can we actually cut a single sheet at sen cut sen like that? And I don't think we can. I think the answer is we can't do that, but we'll find out. So we're using 3 millimeter clear polycarbonate. We're using polycarbonate because it is incredibly, what's the word? Tough. It is the opposite of acrylic. It is not brittle. So you really, you actually, with at room temperature, you really can't just like crack it. It's super robust. Have I used PCB way? No, I haven't, because let's reindustrialize America. Also, Sencut Sen's awesome and fast. They actually reached out to me for a sponsorship, and it was really, really hard to get. So, I mean, just communicating was really tough. I think they have so many sponsorships that they They just have too much going on. Like they have too many people they're sponsoring. So it's hard to keep those relationships quality, I imagine. I mean, it would be hard for me if I was in their shoes. Okay. So the maximum part size actually is pretty close. That is not bad. So we only have one of the dimensions we're off by. That's fantastic, actually. So we can make this out of a single sheet per side, which is super, super simple. I don't need to partner with a 3D printing company actually because I have a 3D printer. It's right there. It's great. I've used I had before I had a 3D printer. I actually used there's a bunch of these online like send cut sends for 3D printing, which are pretty decent, like price wise. It's just you can't. I mean, a 3D printer is like what $400, and it takes. I mean, they're so good now that you don't have to actually maintain them really. I haven't maintained. Well, I have maintained mine actually. That's not fair, but it took 2 years before I had to actually switch out a part. So it's pretty good. Okay, so we're getting close. So this has to be 760, not 800. So what happens if we make this? Oof, no, we can't really come down on that, can we? What happens? Let's say 760. Yeah, we're just below it. Well, actually, we can buy that extra distance with the angle. We'll be gapped, but we don't need to be air or watertight. So, but yeah, I mean, $300 that you can't beat it. And again, the a $300 the thing isn't just cost. I remember I was a member of a makerspace 10 years ago, and it was a nightmare to maintain. I mean, this is I think they had Ultimaker 2s, and they were not cheap. I think they were a couple grand. The problem wasn't the cost. The problem was they broke every couple days. So you were just constantly maintaining them. Today you can go buy, I mean, pretty much any 3D printer for $400, and you're guaranteed to have it for a couple of years before you have to replace a part. So, and it doesn't require tuning. That was the big one too. The tuning was a nightmare. Okay, so how do we get this going? So we'll actually pull this down. I think we'll call it 40. And then we'll actually pull up, nope, I want diagonal. Now we'll have this square represent the bicarb. Now we're there, actually. So if we can engage this, All right, so we'll do this. We're going to have 10, we'll call it 20 millimeters of engagement with the angle below it. All right, so this kind of represents, well, I'll just draw it out. How about that? I will just draw it out. So this is going to come across, and this will be 3 millimeters. Because that's the thickness of the poly. Well, no, that's not going to be 3. That's going to be 3.18 because we're going to make that out of aluminum. So now I can draw this. So this will look like this. Actually, let's get those screw holes in there too. Okay, so and we'll pattern these. 25 from the side, and then we'll actually mirror this off to the other side. Show you a trick for how to draw patterned holes in an assembly for a fixed distance. So you essentially mirror this side about the center, if it works. There we go. And then you can then get your distance between these two holes, and that's going to be your pattern size. And we are at 950. So now I can draw the hole we're going to pattern, and we'll use M5 screws. Actually, I've got a ton of M4 around, so we'll use M4. Now we're going to pattern this. We'll say we want 8 holes, and we want a distance. Actually, we want this linear. 8. So it'll be 4 per side. That's too much. We'll do 6. And then we'll do negative 950 here. 950, not 959. Boom. Okay. Did we get the right amount? Why didn't that work? Oh, I used spacing, not distance. There we go. All right, so there are our holes. And so, curious, what is the distance between them? So 190 will be the patterning distance we'll use from now on. All right, so now we can extrude this. So here's our polycarb sheet, which fits the DFM guidelines at 3 millimeters. And then here's our angle. And then we'll do this side too. Join these. Oh, we also got to get this. Mess that up. So we'll get that Boolean. I mean, we'll get the extrusion corrected. There we go. All right. So we actually want to get these holes patterned down here too. It's the best way to do that. Let's see. If we make this symmetric, it's 60. This is not 60. It's 50. What are we doing? What are we doing here? We're all right. Yeah, we're all right. All right, so we can actually just mirror this, I think. Yeah, this isn't going to be pretty, and yeah, don't care. We're going to mirror this. No. Wrong. Should be right. Sorry, no, we're not going to mirror it. We're going to pattern it. Or, I'm sorry, we're going to move it so we can create the symmetry plane and then slice this. And now we'll be able to make this part symmetric, essentially. So it doesn't matter how you arrange this. You have the same part no matter what, which is going to matter later. And then we'll add the radii. So this was 3.18. And this will be 2 times that. It's not 2 times, that's 1 times. Okay, we'll add some radii. Okay, that's our angle. And so this is our polycarb, which bolts on here, which is just double checking the distances here. This should be less than 1,000, which which it is, or 1100, and this should be less than 760 something, which well, it is 760. And going back to the symmetry thing, I'm actually gonna, well, first things first, let's actually make this clear so we can see clearly, pardon the pun, what we're doing when we actually get to the assembly level. There we go. So now when we show this, we can actually kind of see through it now. Didn't work. Why? Works in visualization. Okay, we'll come back to that later. Actually, if we change this to, maybe it's, I think we have the wrong material. Oh, I selected a face, that's why. If we do clear glass totally, does that work? There we go. Okay, and so now, sticking with the theme of symmetry, we should be able to isolate this part and then actually create some midplanes. That we can use. I'm symmetrical about, okay, yeah, we can create some midplanes. And I should be able to mirror these around and not have to redraw the rest of these features. So I'm just slicing this now. And let's see, do a sanity check on this. We'll slice it into quarters. So now let's, if we mirror this, it should look the same over here, which it does. Great. And we actually want to rotate this, not just, yeah, we want to rotate this actually. Again, the reason why I'm doing this is because I'm trying to maintain symmetry so that when we go to use these parts everywhere else, we don't have to make sure we have the correct panel because they're all going to be the correct panel. This is just, in terms of general mechanical engineering design, this is good practice. You want to do the opposite of pokey-yoke until you have a reason to do it. So we don't want pokey-yoke, we want worky-worky. 360, see if this works. It doesn't, because it's not square. Of course that doesn't work. Duh. But, okay, I know what. Because we have to build vertically the right way to do this first. So let me do that. So I think we said, actually we'll just draw it. So we are, how off of this? What's the distance? I might be overthinking this. I think I'm overthinking this. Yeah, I'm overthinking this. We'll just, we'll get to the sides in a second. Okay, checks out. Okay. Seems to work. We're going to want to tie these together potentially. But we don't need these giant angles for that. Yeah, I don't think we need these giant angles for that. Okay. but I will copy the design of the angle. So I'm actually just going to modify these angles. Actually, to keep it clear, we can make them out of polycarb. That'd be easier. Yeah, the behavior of the pendulum would be chaotic. You can't predict, well, you can predict it. We live in a deterministic universe. At least at the Newtonian scale. But knowing all the true initial conditions is the hard part. So let's just get this. I want to model. Let's model this side, and then we'll be able to pattern out the rest. So let's make a joint here with, these will be super simple. We'll just use little angles essentially. Let's see how this actually works out. Before I do that, we get these radii there. So I think we can actually just rotate this. Before I forget, give clearance to that polycarb. Let's move this out. Okay. And then we can pattern this over, I believe. Which almost worked. Come out the thickness. Okay. I think that works. Yes. Now we can join these two. Okay. We really don't have a good intuition as to how big this has to be. So we're just going to kind of spitball it. Now these have to be 3 because that's the thickness of the polycarb. Should we use thicker polycarb? 1/8 inch. I think 1/8 inch is fine. I think. Okay. What's the minimum part size? We're good. We're bigger than 25. Okay. And I think we're just gonna, yeah. It was 10 and 5.2. Okay. So there's our little angle detail. So we should be able to pull this down. And this is going to join the corners. Yeah. Looks about right. Okay, and so I think we can just mirror that down now. Yeah. These also become clear. And then we need to slice these. Okay, so does this should be symmetrical still. We'll find out when we pattern around the rest. I think we'll be okay. This part needs to change, actually, because it's going to interfere with this side. But these distances, like this is not a square, so this is going to have to change anyways, I think. Let's see. This is 963, and then this was 1000, so it's not a perfect square. Which is a little silly, actually. Why is that? So this is 1000. This is almost 1000. We'll just change that to be 1000. So now it should be 1000. Great. Okay. And so now that makes these parts the same. First we slice this. So now we're getting something that we can start to pattern around. It doesn't look like we're close to done, but we are. So how do we get this in place? I guess a rough transform could work. Yeah, we know that has to be 3 off. I guess we could do that. Let's see. Hmm. Oh, we can just translate that's going to work. So yeah, this should put in the right place. Okay, and now you can see that interference. But this should be 3 off here. Yeah, okay. So the way we fix this is what do we do here? I think we slice this. Yeah, I think we slice this. Step back in time real quick to make that change. Let's see. Yeah, 45-degree angle, that's right. That's what we're gonna do. That is correct. That's a bingo. Although it does mean we lose this mounting hole, but I don't. It means a couple things. One is we lose the mounting hole, which I don't care too much about. Yeah, I don't care too much about that, frankly. So. Okay. Now we mirror that over to the other side. Actually, this is going to be easier if we just slice this and remirror it. Nope, that was a mirror. You slice first. I changed my keyboard binding, so I'm a little slow today. So we got to clean this up. That isn't correct. Why isn't that correct? This has to be perpendicular to this edge, that's why. So what is that angle? 135. Duh. So we'll do, yeah, that makes sense, duh. Actually, how do we move that relative to this face? I think we have to kill this fillet. Right? Yeah, there we go. I don't know why that's annoying me as much as it is, but oh, I know why. Okay. Yeah, this needs to come out of it. It's a cutting relief, essentially. Yeah, okay. Okay, there we go. That should work. If we roll this forward, why did that break? Cool. Very close here, but that's okay. This is changeable. So we're going to move this control box. Close. Okay. Then this needs to shift. Good enough. Okay. All right, so now we should be able to mirror all of this, and this should all just propagate. First, I have to fix this. Where's that midplane? There it is. Okay. This should be this easy, but I do want to get the screw holes in first. I'm sorry, I want to get the screws in first. I think that's going to work. Do I really need polycarbonate up top? Yes, actually, yes, I do. Yes. Why not? When in doubt, be safer than you think you need to be. All right, let me get the screws in here. Some M4 screws lying around. I think that was this. Need screws and nuts. M6. M6. Why are these encoders in the wrong place? Oh, I know why. Because when I moved the control box, I moved the encoders too. Stupid. I think that's right. Yes. Do I not have any M4 nuts here? Whatever, I'm just going to brute force it. So M6, scale it 4 to 6. Might have done that with the wrong number. There we go. So now we get to copy these everywhere. Actually, we want them to go the other way. For hashtag aesthetics. So the cool thing is we should be able to quickly just pattern these. Because I know what that distance is. I think we said it was 190. So we're going to have 3 at a spacing of 190. Great. And then we mirror these. And then bring them over here. Okay. Finally, we just need these 4 holes and then we're done with these screws. Make a copy. Okay. Is there a fast way to do this? I think there is. There we go. All right, so now we should be able to pattern this around, and this should be pretty much done, sans the threads we're going to have to add on the plates. By threads, I mean actually we're probably going to do through holes, now that I'm thinking about it. So how does this work? I think we just mirror. Yeah, I think we just mirror this. Let's see if mirroring works. Mirroring should work. Why didn't it work? The screws don't want to mirror, and I don't know why. Nope, they do now. And then we join this. This should be good. Looks good. All right, we do the same for the other side, and then we should be able to finish out the everything except for the top. This would finish out everything except for the top. See if that breaks it. Yeah, it doesn't want to pattern the screws with the polycarb. I don't understand why that is. I think I missed a face. Okay, so in theory, we should be able to rotate all of this 180. Gonna nest this into a folder called enclosure for now. Make it easier to work with. So 180 at 2 should make this work, which is also a sign that we actually did the symmetry correctly, if this works. I'll clear history after this operation. Let's speed it up. Okay. It looks, so the operation worked, but something is not correct. Oh, the center point is not correct, which makes sense. The center rotation is incorrect. I mean, kind of knew that was going to happen. Hmm. How do I fix that? I wonder why this operation is so heavy. While we wait for that, choose a tube. 1/16 inch square tube sounds good. Yeah. Maybe we go to 3x3. Surprised they don't have 2x2. All right, so we're gonna do this. I'm just gonna copy this and place it in the right place. That should work. I think there's something wrong with that screw geometry. That's why it's taking so long. Yeah, there's something going on with this channel. Oh, maybe it's because it's transparent. Yeah, I really have no idea why. It's bugging out. It's the first time I've seen this. So hopefully this auto places correctly. If this auto places correctly, that means we assumed all of the symmetries correct. Assumed all of the symmetries correctly. And it looks right, roughly speaking. Yes, I think that's about right. I mean, I think that's right. That's great. Well, that simplifies a lot of this, since that's right. Okay, great. There's the base of our enclosure. We still have to do the door. We'll do the top first, and then we'll be good. So we are going to have to split the top into two, I think, because of that minimum part size, which was, let's see, maximum part size, I should say. It was this number. So if I draw a rectangle, this number, which was 1100 by 762, call it 760. This is the maximum we can make this part. You can see clearly that will not take care of everything. So we have to split this into two, essentially. Unless, no, we're going to have to split this into two. So how do we do that? I guess we just create two sheets. Just keep it simple. Yeah, I mean, it's going to be that. It's going to be that. Creating a symmetry point here. So I can mirror all of this. Oh, that's not good. Yeah, I guess it's not a perfect square, so duh. that does mean that this is no longer symmetric, which could not be a big deal. But I mean, we're not mass producing this thing, so it doesn't really make a difference. Actually, let's give ourselves a little bit of clearance here, so that when these two join, they don't butt up against each other. Give it 2 millimeters. So now, should be able to mirror that. That does not look right. Oh, it's because the center point again was off. Okay, can't mirror that. Okay, now we should be able to extrude this without any pain. The 3 millimeters for the poly. Okay. Hide the sketch. Fix that Boolean from union to new body, and then change this material to polycarb so we can see through it. And there's our parts. Let's add some healthy radii. And then we mirror. And now we have a functioning enclosure. We have to add hardware there, but yeah, we will do that. We should find the midpoint between these two to simplify this. We mirror this. So this is going to be unsupported in the middle. I don't really know what to do about that. I guess it isn't that long of a distance, and it is 3 millimeter polycarb, but it's not great. It's not great. Yeah, I wonder if there's a way we can stiffen that. Problem is, if we stiffen it, we eat into the clearance for the pendulum. So I don't know that I want to add a stiffener. Oh, I could add a 90-degree bend. How about that? That would actually stiffen it up. No, but it would add it. Actually, we'll add a 90-degree bend. Yeah, we'll add a 90-degree bend, and we'll add it to. We'll have it poke out of the of the um, of the enclosure, and that will stiffen it up without eating into the clearance for the pendulum. So, step back in history. I don't know what a Hoffman box is. Hope it's not inappropriate. Hoffman box. No. Technically, there are electronics in it, but this is a science experiment that we're containing within an enclosure. So it is a box, but it's not a Hoffman box. It's a Hoffman box, I guess, in a bit in the sense in that we have electronics inside, like the control. And actually, no, I'll keep power. Yeah, I'm going to keep power on the outside. So we'll add that bend now. I'm going to do this as ugly as you can. The parametric mind cannot comprehend. They tremble in fear at the speed with which we cobble together geometry. And that makes it even more fun. And so again, this is not doing anything functionally other than to provide stiffness to that, what is essentially it's not a cantilever, but it's a pretty big unsupported section between the two sides of the two supports essentially. So, yep, it's just for stiffness. So now when I set this on top, these 90 degrees, these 90-degree bends act as a, if you really want to get into it, we can. Actually, let's get into it. What is the science behind why this 90-degree bend makes this not deflect here at the center? Here's why. So the reason for that is if you were to look at this, if you were to analyze this bending, how do we look at this? Yeah, okay. So this is the length of the member. We're going to look at the cross section of that member. So before the design change, the member was just a flat plate, right? And the centroid of that cross section was right in the middle of that rectangle. And the resistance to bending, I, or the second moment of area, is BH cubed over 12. H here, super, 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 super small. It's 3 millimeters. But when you add a 90-degree bend to it, like so, your center axis moves here, and your H gets super, super big. And so your stiffness, essentially, this isn't stiffness, but you can think of it that way, just went up by a factor of H cubed. So that is much, much stiffer. It's much betterer, as an engineer would say. So it's funny, we all intuit that, but describing it mathematically at least helps you think through, why it is. Okay, so there's our enclosure. And it took us an hour and a half. Actually, it's not moment of inertia. Trust me. It's not moment of inertia. It's very annoying. And it's not really anyone's fault, but engineers over the last, I don't know, 5 decades have totally botched the nomenclature for second moment of area. So moment of inertia is a property of volumes with mass, and that's the resistance to acceleration, angular acceleration. Second moment of area, which is what we were just talking about, has the notation I, which is very annoying, but it's technically called the second moment of area, or the second area moment, or the quadratic moment of area, or the area moment of inertia. So you're almost there. It's the areal moment of inertia. And so this is super stupid. It's very, very stupid. And here we are. Oh, and it gets even more complicated. So not only is this not moment of inertia, and not only does it have the same notation as moment of inertia with the uppercase I, technically it's the same thing, but not the same thing as polar moment of inertia, which is the notation J, or second polar moment of inertia, which is essentially just saying, okay, what is the plane by which this rotates? So it's really just I sub z. But in mechanics of solids books, you'll see J as the notation and not I sub z. So all that to say, never trust an engineer, because they just complicate stuff. We just complicate stuff. Like, this could have been way easier, but we insisted that we make this as complicated as possible and make it so you have to Google this anytime you use it. Kidding, you should trust engineers, but only when they know what they're talking about. That's the trick. Okay, so that is an enclosure. We need to add a door to this. Where do we add a door? I thought adding a door would be more useful, but the thing is, this is so far away from here that it would have to be a pretty big door to make it usefully accessible. I was going to use a latch. Actually, I have a bunch of these latches laying around from the Tumblr project, so I was going to repurpose them. Let's see. These latches right here. But now that I'm thinking about it, that requires a hinge, and that seems maybe a little too complicated. So instead, is there a more clever way we could do this? Like, for instance, could it just be a sliding door that you drop in place? Speaking out loud, I'm thinking, no, that is something we can't do. Because what if the box tips over and then the hatch just falls out? Do we just add access holes? I don't know. So the reason why I'm debating how we're going to do this door thing is because here's the video from the paper we're recreating. So you can see why I'm spooked. So they actually had a 16th of the torque and power in their motor that we do, because they got rid of that reduction system. So if the thing goes haywire, I don't want to be anywhere near it. And that's what the safety hatch is for. The reason why we need potentially some system of like a door is because we want to prove that what they did in the paper here is real. So what they did was they showed that, hey, when you perturb the system with some random input, i.e. a dude or dudette tapping the pendulum with an implement, if you will, broomstick, banana, whatever, um, that the system can recover. You can see that here. This is not programmatic. Like, this is literally an agent that they trained using reinforcement learning. So what they do is, what they're doing here is they're showing, hey, when you train our agent, not only does it maintain positional control, you can actually induce some instability, and it will recover very quickly. That's one of the novel parts of this paper, is that they've implemented transition control plus recovery to any of the four states. So I need to be able to get into it and tap it. And again, the reason why we have an enclosure and they don't is because they're in a lab. Their motor is a 16th of the power of mine. And I'm not in a lab, and I have a 16 times more powerful motor. Pictured behind me, which you can almost see. But so we have to find a way to be able to perturb the system. And that requires a door or some access hole or something to get into it. I've half a mind to just not put in the top, but I'm nervous about that. Three arms. A triple. So I did look up triple inverted pendulums. They do exist, but I don't know that they are reinforcement learning agent controlled. First of all, I don't know if they have rotary triple pendulums. Is this a double or triple? This is a single pendulum. Easy. Anyone can do a single pendulum. Easy peasy. See, this is the part of YouTube that's great. Forget, what is this? That's awesome. It's like purposely spinning it. I don't know that I'd be the first. I don't know that YouTube is an exhaustive. Okay, so they did it with a linear motion system. They didn't do it with a rotary system. That's what this is. And they're not using they're using a deterministic algorithm. They're not like reinforcement learning this thing. I gotta find out the term for that. Single pendulum, rotary double inverted pendulum, triple inverted pendulum, and a cart. Yeah, I mean, the cart pull problem is like solved. Linear. Yeah, but see, this is a linear system. This is what we. I mean, this is bonkers. Like, it's funny. These videos make it look so easy, but it isn't until you actually get one of these in your hand and try to do it for yourself that you realize how hard it is. Yeah, I don't think a rotary version of this exists yet. Hey, look, it's me. It's us. Yeah, we'll do that eventually. If this works easily, then we'll go to 3. I don't think we'll be able to do 3 though, because I'm barely making 1 millisecond response time on the control loop. Okay. So hatch. Hatch, hatch, hatch. Do we... Uh, huh. Yeah. Guess we just put a giant door on this side. That way well, yeah, I guess we just need a door. This is not, no filters. This is all reinforcement learning. There's no control algorithm outside of an agent I trained. So you can find the code here, but this is an implementation of the of the paper. Essentially, trained an agent to, or an actor. I trained an actor to over 5 million episodes learn how to balance the pendulum in four states. You can actually go run this for yourself and try it out. The actor is in the repo as well. But there's no Kalman filters, none of that stuff. This is just machine learning. All right. I'm just going to slap a door on the side, get some tubes for the bottom of the frame, and then I think that's it. And I'll do it on this side because that'll give me control to access to the control box, obviously. Okay. Optimize timing. I don't know what you mean by timing. The system just knows. Well, it's working in software. Part of the nuance of the paper, part of the novelty of the paper is that they demonstrated that you can transition from simulation to real world by mapping the parameters of the system super accurately. So the weight of the pendulum, the distance of the centroid of the pendulum, of the mass of the pendulum away from the axis of rotation for both pendulums. So all of the parameters that go into the dynamics that determine the behavior of the system. If you map those, if you get those super accurate, and then you, for fixed input, read back the encoder positions. In other words, go train your model. Go put a fixed input into the motor. Read back the encoders. Take that data. In other words, you get a chart that says, here's where we predicted the encoders to be in terms of angular position. This is where they actually were. You then regress the adjusted parameters. And then I believe you retrain the model on those adjusted parameters. Then you deploy that. Then you deploy that model, that actor, retrained with the new parameters. I have to reread the paper. I don't think I don't think you then feed the new parameters into the old model. I think you have to retrain it. I believe that's what they did. This is all on the website that's linked to from the GitHub, by the way. So, actually, let's just go to the abstract. mathematical modeling and parameter estimation. High resolution sensors, yada yada. This is the algorithm this is the training process for the actor. TQC. Okay, the learn policy is directly deployed on hardware without additional tuning or calibration. Okay, so you don't retrain it. That's right. Okay. So you don't retrain the model or the actor. You just give it the adjusted parameters. And then because during training they randomize the parameters during training, the actor is robust enough to take any adjusted parameters not any, but within reason, adjusted parameters you gave to it. Parameters being things like coefficient of friction for the bearings, the actual position for the moments of inertia, like I talked about, or the distance of the centroid away from the rotational axis. Once you give it those adjusted parameters, you don't have to retrain it. It's just able to um, just take that as input. And I'll show you real quick where that is. So it's actually an interesting chart, if I can find it. Where is it? Here it is. Okay. This is what I was talking about. So you give it a fixed input, which is, hey, rotate. Yeah, rotate. Here's the fixed input in terms of acceleration. That's sent to the motor. And this is the blue line is what we expect the encoders to be. And the simulation is what we expect the encoders to actually be, and real is the blue line, which shows hey, actually you're slightly off because these 5 parameters are incorrect, right? And so then you are able to regress corrected parameters that then line up these two curves. Fundamentally, then because it's a single axis of motion, it's pretty good. So reaction time for the control loop around 1 millisecond. How do you optimize that? Can you refine control, or is it described? I can't refine control. It's only through the actor. Is it described? I'm not sure what you mean by described, as in if you mean it's fed out through encoders, each axis of motion is indeed read, but I'm not like printing it out. I mean, it's either the pendulum balances or it doesn't balance. That's like, that's it. 1 millisecond. Okay. The reason why it's 1 millisecond is because that's what the paper was able to achieve with their hardware setup. And 1 millisecond is the sample time for the actual training. So what I did was I ran, I've only run the output control loops so far. And that's sub 1 millisecond. It's on the order of, I think it's somewhere around a 50th of or less millisecond. Now, I haven't taken into account the input back from I know that I can get sub 1 millisecond computation, and that sounds trivial, but the issue is that the hardware I'm running on is pretty weak, and so I wanted to make sure that that was possible. So I am able to get to sub 1 millisecond compute on inference on the actor. The question is going to become, will it slow down? Or in other words, will that start to creep up closer to the 1 millisecond if I start taking encoder inputs? I don't think it will matter. I think if you look at the computational load, I might actually go into this later, but if you look at the actual computational load, it's like 99% doing inference on CPU. I'm assuming that it will be trivial to read encoder information on some GPIO pins. And so if I'm my understanding or my assumption is that if I can keep onboard compute for inference sub 1 millisecond, I can then rely on timers, kernel level timers, to wait until 1 millisecond intervals to issue commands. That falls apart if my compute takes longer than 1 millisecond, right? But as long as I keep it below 1 millisecond, I'm fine. And I was seeing commands issued. I mean, honestly, what is it called? A picosecond? What's a hundredth of a millisecond? That's not a picosecond, it's a nanosecond. It's on the order of nanoseconds on a lot of the steps. So long story short, inference is the limiting factor. Inference was on the order of nanoseconds, not milliseconds. So my assumption is that I will be able to wait. The assumption is that I will be able to get the controller to wait for millisecond intervals to issue commands to the motor. That's what they did in the paper. So I don't know if that answers your question. Maybe I didn't understand it, but there you go. And just double checking, do they actually retrain? I'm curious about this now. To validate the physical consistency, they have a fixed input, then they measure alpha and beta trajectories, which are the encoders. Okay, I think I have to go further down to see where they actually feed in that regression. Prior to the deploying of the train policy. Nope, that's not it. Yeah, this is going to make for good streaming, but I'll double check that later. Yeah, this is the video we already saw. Kind of cool. You can actually, when it's in episode 3, which is the hard one, I don't think these are millisecond response times. I mean, watch it vibrate. It looks like 10 millisecond response time. So they said 1 millisecond in the paper, but it doesn't look like 1 millisecond to be. I mean, that's 0, 1. That's like 10 milliseconds. Anyways. Okay, that's it. I'm not sure if I'm going to string the rest of the design of this enclosure. I don't know how compelling it is. And I'm really interested in getting this out the door as quickly as possible. So we'll see.